AQA, A-level physics. This is my second waves video, again very GCSE, longitudinal and transverse waves. This is a bit of the specification that we're going to be looking at. So, longitudinal waves, transverse waves, there's two key words. Longitudinal, we're talking parallel. Transverse, we're talking perpendicular. Longitudinal waves, the oscillations are parallel to the direction of propagation. Transverse, the oscillations are perpendicular at right angles to the direction of propagation. In terms of longitudinal waves, the wave is sound. Sound is longitudinal. There's not many others. I mean, sound traveling through a solid, there's a type of earthquake wave called a P wave. You might remember P and S. But basically sound is the longitudinal wave. Transverse waves, you've got water waves, you've got S waves I mentioned, and then all of the electromagnetic waves. Electromagnetic waves are transverse. Bit more about sound. I didn't do this animation. It's University of Southampton it is. Sound is a longitudinal wave. The air molecules, look at the animation, oscillate parallel to the direction of propagation. We have regions of high and low pressure. So where it looks denser, the darker bits, they're high pressure and they're called compressions. And you can see these compressions traveling through the gas. Compressions and rarefactions. The speed of sound in air is about 330 meters per second. Depends on temperature and humidity and one or two things. It's about 330. Now, electromagnetic waves consist of oscillating electric fields and magnetic fields. And the electric field, E, is at right angles to the magnetic field, B. B, capital B, magnetic fields. In this particular diagram, I've got the electric field as being in a vertical plane and the magnetic field in a horizontal plane. It doesn't have to be like that. It's just on this particular diagram. Neither of these oscillating fields can exist without the other. When you've done more about kind of electromagnetic induction and stuff, you'll understand why. They can travel through a vacuum, so they don't need a medium. In a vacuum, they travel at 3 times 10 to the 8 meters per second. And that guy there, James Clerk Maxwell, a very, very clever bloke, he actually worked out the speed of electromagnetic waves before anybody measured it successfully. And this idea of an oscillating electric field at right angles to an oscillating magnetic field, which is why they're called electromagnetic waves. What do you need to know about the different waves? Well, radio has the biggest wavelength and the lowest frequency. Gamma has the smallest wavelength, the highest frequency. You should definitely be able to write that list. In terms of wavelength, this is what I remember, which serves me well. So radio, big wavelengths, can be several kilometers, down to about 10 centimeters. You know, the short wave, medium wave, long wave. There's lots of different kinds of radio waves. Microwaves are typically a few centimeters. In your microwave oven, it's about 12 centimeters. The microwaves for your satellite television is about 3 centimeters. Infrared, we're kind of talking millimeters. Then Roy G. Biv. Red has the biggest wavelength. It's about 700 nanometers. Violet's about 380 nanometers. Okay, so Roy G. Biv, and then ultraviolet. I just remember it's less than violet. X-rays are about the size of atoms, so about 10 to the minus 10 meters, and then gamma can be very, very small, from about 10 to the minus 11, 10 to the minus 12, 13, Okay, so that's what I remember about the wavelengths. This is important, polarized and unpolarized. Now, if the wave is polarized, so we're talking electromagnetic waves here. If an electromagnetic wave is polarized, then the electric field oscillates in one plane only. Could you learn that sentence? Write it down and learn it. Okay, it's very likely you'll have to regurgitate that. The electric field oscillates in one plane only. For example, vertically. I'm not bothered about the magnetic field, just the electric field. If it's unpolarized, then the electric field oscillates in multiple planes. Some of it is vertical, some of it is horizontal. Okay, so it has vertical and horizontal components. So the electric field is all over the place. Okay, so learn those definitions. This is what we mean by polarized and unpolarized. Now, this is a polarizing filter. The specification actually calls it a Polaroid, which is actually a brand name for a type of camera. But it's a polarizing filter because what it does, it absorbs one of the components of the electric field and transmits the other. So this particular polarizing filter, you should see it's absorbing the vertical component and the horizontal component is getting through. So it absorbs one of the components and transmits the other. Transmits means it goes through it. Two polarizing filters at right angles, and we call them cross Polaroids, yeah, would absorb both components, so no light is transmitted. Hopefully you've had a chance to play with some of these. If not, then get your 3D glasses from the cinema and take the filters out and have a little play with them. Have a go at this question yourself, and I'll talk about it in 3, 2, 1. In the position shown below, the microwave receiver picks up a strong signal. Which of the following statements are true? So the electric field of the transmitted wave oscillate in a vertical plane. And the answer is that is false. Okay, I'm looking at these, they call them prison bars, these metal rods. And basically, those metal rods would absorb a vertical electric field. So the electric field must be horizontal. When the metal bars are rotated 180 degrees, then the signal strength received gradually falls to 0, and that's false. As you rotate it through 90 degrees, it will fall to 0, and then another 90 degrees, it will get stronger again. So that's false. This can be used to demonstrate that microwaves from the transmitter are polarized, and that is true. Longitudinal waves can't be polarized, okay? Only transverse waves. Uses of polarizing filters. When light reflects off water, it becomes polarized. And so if you're looking at water, a lot of the light that you see is polarized light. And sometimes that we call it glare, and we don't want to see it. So you wear your special Polaroid sunglasses, or the camera person puts a polarizing filter on the camera, and you get a better picture when you're photographing water or other stuff. So polarizing filters. The top right one, it can be used in stress analysis. If you want to know the regions where there is the most stress on a component, what you do is you make it out of thin plastic, and then you look at it through cross Polaroids, and the plastic kind of rotates the plane of polarization, and you end up with groovy colors because different wavelengths are polarized by different amounts. You don't need to know very much about that at all. Okay. you have some polarizing filters on your LCD, your liquid crystal display on your calculator. I'm not going to talk loads and loads about how LCDs work, but if you're interested, look it up. A calculator uses a polarizing filter because the liquid crystals, when you put a voltage across them, they line up and they become like polarizing filters. And then bottom right is your cinema 3D glasses. When you see a film, a 3D film, you're actually looking at two different films. One film goes in one eye and the other film goes in the other eye. How are they separated? Well, one of the lenses, if you can call it a lens, one of the filters is one way, the other filter is at 90 degrees. And so one film goes in one eye, the other film goes in the other eye. You see 3D. Your TV aerial should be aligned so that it matches the plane of polarization of the transmitted waves. So basically there you've got a transmitter and you've got your receiver is your TV aerial, and it should be aligned so that it matches just like the microwave one. Okay, I do believe they actually send out the waves so that they're at an angle of 45 degrees, and then you've got a better chance of picking something up.